started.
You already started?
Yeah.
Oh, you may suck it now. You suck, Chucky. You suck.
We are recording here, so
Yeah.
I don't want you to say that.
Okay.
Okay.
I'm not saying that. I'm gonna say.
The waves. Every wave has a length. Okay, any sound wave, light wave, whatever, has a length to it. And that length can be important. Okay? The wave of, we actually have different sound frequencies that I actually did with the phone. We'll pause here for a second. The general audible range for sound, okay, that you can hear, it will be between 20 hertz to 20,000 hertz. Okay? So let's see what we can hear. That is 144 hertz. Okay. 20 to 20,000 hertz, but really 50 hertz we heard for that deep bass. Okay, so that deep bass you want was 50 hertz. Now, there's a formula that I'm going to show you in a second, but really, just so you know the numbers, for 50 hertz, to hear that deep bass, the wavelength of 50 hertz is 7 meters. Okay? Which means, if this wave, if we drew this wave for that bass, the distance between these 2 points would be 7 meters away. Okay? So when you have that subwoofer in the back of your car that's getting that deep bass going and you love it, think about how far away your speaker could be from you. Maybe 2 meters?
Yeah.
Maybe if you got a long car somehow, maybe, I don't know, 2.5 meters, 3 meters? Yeah. So you're not enjoying that bass as much as everyone else around you is. Has anyone been pulled over and received a ticket for having a car too loud, having their car stereo too loud?
I usually turn it down when I see the cops.
Okay, good call. But you'll see in residential areas, police will be out with a decibel reader just to see how loud your car is. And believe it or not, so things like your bass could be louder for them than it is for you. Okay, because you need to have that full wavelength to be able to hear some of those sounds. With like subwoofers, have you ever been parked at a light and you hear that subwoofer of a car 3 cars behind you? Yeah. Well, that's because the wavelength will be hitting you. All right. Any questions on this? Period we already talked about before was with rotational motion. Period was the time it takes for one complete cycle. Same thing. So the time it takes for a sound to go in and out, or time it takes for a speaker, that woofer to go in and out, would be the period. Okay, the number of seconds, or the number of cycles in and out a woofer does each second is the frequency. So when you have that bass, that 50 hertz bass that we heard, that speaker still has to go in and out 50 times for you to hear. You're not going to be able to hear it if it goes every second. That's too low of a frequency for you to hear. Okay. So frequency and period are the same things we've already learned. Alrighty. Really should be fired. Okay.
Thank you.
Right here, this frequency, whatever it is, we only have 1/2 of a wavelength because we only have one antinode, one peak. Okay, a full wavelength would have one peak and one valley at the same time. So let me see if I can do a full wavelength here. If I double the frequency, ready? I'm going to double the frequency. Not yet, not yet. Oh, there we go. See that? This is a full wavelength because I have a peak and a valley. And that point in the middle, see that point in the middle you're getting? That doesn't move? That's the node. Okay? So these are nodes. The points that don't move are nodes. The peaks and the valleys are the antinodes. Think I could do 3 times the frequency? I had it. Oh, I lost it. There we go. Yeah? I got it?
Yeah.
Alright. You'll have on, say, a worksheet today, say a daily quiz next class, say on the test to measure the wavelength. You'll need to measure the wavelength here. Okay? Whoops, I didn't kill my phone. Alright. you need to just find, now you can measure anywhere here, but it has to be two identical points. If I ask for the amplitude, that will not be the entire height of the wave, it'll be from the node height to the peak. So the amplitude here is that length. So velocity of any sound will equal frequency times the wavelength. Alright? And yes, you could do the cheater equation like before and say V equals F times lambda like that if you'd like. Okay, and put your hand over what you need. We will pause our recording there. Are we recording now?
Yeah.
Good job.
Yeah.
Wonderful. Okay. Two types of waves I want you to remember. Transverse and longitudinal. Okay? And what I say is that the displacement, perpendicular, propagation, what I'm saying is this. Okay. Here's my wave again. Now, a transverse wave will mean that the material that the wave is going through, am I in it? Is he in it? Is anything in it? Okay. The material that the wave is going through will be up and down while the wave goes across, so they're perpendicular. So here is a transverse wave. Ready? See that? Let's see it again.
It comes back.
Well, no, but see how the material, the slinky, goes up and down as it moves across. So that the little hump of the slinky goes across. It goes up and down. The material goes up and down. Now, so that would be transverse. Longitudinal is when the material goes in the same direction. So if I pinch a little bit of the slinky here, okay, the slinky here gets pinched, gets compressed, that bumps into here, that gets compressed, that gets into here, and you're not recording any of this, that bumps into here. Yeah, but you're not filming me. Okay, that bumps into here, okay, bumps into there. So this is what sound would be like, okay? The vibrations coming out of my mouth would bump into air here, which would then bump into the air there and get compressed. Then that air would bump into this air and get compressed, and so on and so forth. And this is what a sound wave would look like. Okay, that's longitudinal, where there's compression that bumps into each other. And the material is moving in the same direction as the wave. Okay, here are better pictures of that. There we go. All right. Transverse, longitudinal. Here we go. Here is transverse. The material goes up and down as the wave moves across. See that? Okay, I'll go back in a second. Okay? So the material goes up and down, but you can see that wave moving across. Can you not? Yes? Okay? Now, here's longitudinal. The air particles bump into those air particles, which bump into those air particles and move along. But you see those lines? See those lines moving along? Yeah. That would be like a sound wave. If we had talked about that 50 hertz sound wave, that bass, these lines would be 7 meters apart as you move along. Okay? You can do this with even people. Okay? If you're at a really crowded concert or something, all right, and you're shoulder to shoulder because it's so crowded, something happens over here, you get bumped. This would be the same thing, the top view of all the people. You'd see all the people bump into each other and move it like a wave. And waves can travel through people. That'd just be another medium. Okay, pause here, and I'll let you record or go back and write down. You're not doing it yet, are you?
Yeah.
That's the lower frequency, I mean the higher frequency. It's a lower frequency. Okay. We get that? We're done? No? We'll wait. Do all waves require medium? What's a medium? A medium is what any kind of wave has to travel through. Okay, so the medium right now is a slinky. The wave is me going up and down with a hand, and the medium is a slinky. Okay? Sound waves, do they require medium?
Yes.
They do. They require air. Okay, so out in space, thank you, sir. Out in space, you cannot hear sound. All right, you could be out in space banging pots and pans together. No one would be able to hear it. Okay, you see the movies with the sci-fi where you hear the laser blasters being fired out in space. That can't happen because you can't hear the sound. All right, sound has to have a medium like air to travel through. Okay? But do all waves require a medium?
Wait.
Yes.
So, if you take your iPod up there and listen to music, you won't be able to hear it?
Correct. Now, in a space shuttle, like in the spaceship, you have air because you need to breathe. So there, you'll have a medium. You have air to listen to sound. But no, you wouldn't be able to hear any sound or listen to music. But obviously, if your head, if your ears are out in a vacuum of space, your head was going to explode before you even got to try to listen.
Can't you hold your breath for a while though first?
I don't think so. I don't know.
You should try it.
Let's look into it. Yeah. Okay. Do all waves require medium? Sound does. However, light is a wave also, and light does not require medium. Okay? If it did, we would not have any light coming from the sun. Okay? That would be a big problem. So light travels through space. There's no medium out there. They actually made up. When they figured out that light was a wave, they made up a medium. They said, well, if it's a wave, it must have something to go through. So it goes through luminiferous ether. Exactly. But there is no such thing as luminiferous ether. They thought there was, but they proved there wasn't. Okay? Light just doesn't need a medium to travel through. Any kind of wave that we call electromagnetic waves, which are light, radio waves, electromagnetic waves, okay, do not require medium. Okay, so yeah, the radio signal that you send out can go through space. Obviously, that's why we can use satellites and talk and communicate with people out in space. Okay, because we don't need a medium for that. You don't need to copy this down word for word, but I want you to understand electromagnetic waves do not require a medium. Okay? Now, again, you just need to know basically the words electromagnetic waves, and they don't require a medium. I want you to see the spectrum. This is the spectrum of electromagnetic waves, from radio waves all the way to gamma rays. Okay? Light is just this little piece here. This little visible light is the spectrum that we know is just a tiny little piece of this visible spectrum. Or, I'm sorry, of the spectrum of electromagnetic waves. Okay? Alright.
We only see that little bit.
You only see this little piece of the whole spectrum of electromagnetic waves, yeah. Kind of like sound waves. Sound waves you hear from 20 hertz to 20,000 hertz, give or take. Okay? There are frequencies out there on the other sides that are inaudible. Okay? This is the spectrum of light, the visible spectrum of light. Okay, but it's all within that wide spectrum, wide range.
Do you know goldfish can see the most light on the spectrum?
I did not know that. Goldfish, huh? Okay, copy that down. Speed of light, speed of sound.
You good?
Yeah. Okay. Alright. Sound actually goes faster the warmer the air is. The base temperature, if it was 0 degrees outside, it would go 331 meters per second. Okay, but the warmer the air gets, the more excited the particles are, sound can travel faster. In general, we're going to say it's about 345 meters per second, sound. Okay? Which is fast, 345 meters per second. We're talking about sound will travel 345 of these each second. That's pretty good. Okay, now, compare that to light though. Light goes 3.0 times 10 to the 8th. 300 million of these each second. So you turn a flashlight on for 1 second and it will travel 300 million of these in that second. That's why obviously when you see the lightning and then you hear it, you know, when you can figure out how far away it is, because it'll be, the light will travel much faster than the sound of the thunder. Okay? Alright, but notice that the temperature will go up. In general, we're going to say 345, but there might be a problem where I say, how fast is the sound going? And you have to put in the temperature, 0.6 times the temperature in Celsius. Okay? So here, the two waves are in phase, and as they pass through, they add up and make a bigger wave. And then they keep going on their way. Okay? Now, if the two waves are out of phase, you would see them cancel out. And I actually have a slide. Send that, send that. Now we have two waves that are going to interfere. They're going to interfere constructively and destructively. Let me wait for here. No. Here's construct. That was just constructively. Now let's get to destructively. Here they are out of phase. Okay? So on two waves. This could be light, this could be sound. Same thing. When they're out of phase and they're about to collide, they can actually cancel each other out. So there would be a point if you're standing between two speakers where you wouldn't actually hear the sound. Okay? Then it keeps going back through on its merry way. And it's good. Alright? Now, here they're going to be in phase. Just like we saw before. They add up. And then keep going. When you have two waves that interfere like that, if they're just slightly out of tune, you can have two frequencies that are slightly out of tune. Here, the two they're in phase, just a little bit of phase, okay? Here, they're out of phase. The peak and the trough are opposite each other. So when you have two things that are in phase at one point, out of phase at another, this would be the orchestra director, has two people playing the trumpet, and he'll hear one frequency, okay? C, the middle C is 261 hertz, all right? So he has one person playing the trumpet. It's in tune at 261 hertz. Then he hears another trumpet that's slightly out of tune. Let's say it's 260 hertz. He'll be able to tell because there will be interference. At times it'll be constructive, and at other times it'll be destructive. Okay? So they'll kind of cancel each other out. Pause it for a second. Here's one trumpet playing the C. Okay? Now, here's another trumpet playing the same note. No difference, right? But if they're slightly out of tune, let's say that second trumpet doesn't play exactly at 261, but now he plays at 263. What's going to happen is there'll be points where they interfere and add up, and points where they interfere and subtract. So that's what I showed the picture of. It's going to be points where they add up, points where they get quieter, and that's what beats are. Okay.
Actually, 3.
Now, resonance. If you've ever played a guitar, let's say you're in a guitar store and you pluck a guitar string. What you'll notice is that another guitar that's just sitting off to the side, that same string on the other guitar will start to vibrate. This is called resonance. When you have two objects that have the same resonant or internal frequency, they can transfer the waves back and forth between each other. Alright, so when you pluck a guitar string and you hear one note, if it matches the note of some other guitar string, that other guitar string will vibrate. Okay? If you have a nice crystal wine glass, you pluck the crystal wine glass, you'll hear a tone. And if it's crystal, it's going to be more pure and have one pure tone. So you pluck that tone, you pluck the glass and you hear a tone. If you sing to that tone, that glass will vibrate. Okay, so, and if you sing loud enough at that resonant frequency, you can cause the wine glass to shatter. Okay? Now, you could have every other tone imaginable, and you can have the music playing as loud as you want. Nothing's going to happen to that wine glass. But once you match it up to the frequency of the glass will start to vibrate, and if you have it loud enough, it'll vibrate enough. The amplitude will be big enough that the glass has to shatter. That's what resonance is. Okay? There was a bridge in Tacoma, Washington, and it was a modern marble. This was, I think, a 50-something, or I don't know.
38.
38? Okay, it was a little different. All right. So, at that point, they built this bridge. All the best engineers in the country are building this bridge. And when they had a light breeze going through, when they started building it, they noticed that the bridge started doing this. Okay? The air traveling through the cables created a resonant frequency. Okay, and since all the cables had the same frequency to it, it caused this thing to vibrate. Okay, and it matched the resonant frequency of the bridge. Kind of like if you're walking across a bridge, when they tell an army when they walk across a bridge to be out of step, because if everyone was in step going across a bridge, it could add to it and make it a bigger vibration and break the bridge that way too. Well, this was just wind. This was wind blowing through the bridge. There was one day where it was a little bit more violent of a windy day. It wasn't like a hurricane or anything, but it was just a windier day. And instead of doing this, it started doing this. And the bridge shattered apart. Okay, we're going to show you a video of that in a second. Alright, before we get to that, there has also been word about, has anyone heard of the brown note?
Yeah.
Okay, alright. That's actually coming from stories from the military that they've been working to create a resonant gun. Okay, and the idea with a resonance gun would be that it would shoot vibration. Instead of shooting you, it would fire vibrations towards you, okay, sound waves that would match the internal resonant frequency of your bowels, just like a wine glass. However, I don't know, I haven't seen G.I. Joe. But, however, the frequency would match your bowels and start vibrating your bowels, so instead of wanting to fight, you'd want to find the closest bathroom. Does that make sense? Okay? Hence the brown note. Now, I don't know if that's true. We have a Mythbusters where they try to do that, and, well, we'll see what happens there. But there's one thing I know is true is this speaker. A bunch of MIT students had created a speaker that, when it pointed directly at you, okay, sound for me is going in all directions. Sound's traveling everywhere because of the frequency. What they found a speaker to do is they could point it only at you, and when it was pointed directly at you, you would hear the sound. As soon as it moved away, you wouldn't hear it anymore. Somebody else would. Okay? But what it was doing was the sound wasn't going out at normal sound audible frequency. It was going out at the resonant frequency of air particles. So what it would do is it would shoot out the sound wave mixed in with where it'll vibrate the sound particles. Okay? So that, or the air particles. So then it would only be in a straight line. So you could hear a speaker, and as soon as the speaker turned somewhere else to the side, you couldn't hear anymore. And I do know they turned that into a weapon, where it's a big speaker, LRAD or something.
Yeah, I've heard one, like, I've got one playing.
Oh, have you?
Yeah.
And so the idea, again, it's really, really loud speaker, but it's not just that it's a loud speaker, but it's going at the resonant frequency of air, so it is more like a laser. It only goes in a straight direction. So you have this really, really loud speaker, so if somebody's coming towards you, they point the speaker at you and say, please stop, and if you don't stop, they turn on this really loud noise and makes you feel sick. Did you feel sick?
Yeah, it's like the loudest thing you've ever heard.
Yeah.
It didn't turn up all over.
And that was from the MIT design. It's from the people that were using it just for speakers. Okay. Resonance. Let's see. Am I good there? I don't want to do... I did Doppler effect with the other ones. Let me do the Tacoma nearest bridge real quick.
Should I pause?
Pause. Sound goes and travels, the nodes of the sound wave travel in all directions. So right now the nodes are going in all directions, just like that picture up there. Okay? So the peaks and valleys just travel away from me in all directions. Now, what happens if I move though? If I move towards you, if you think about those peaks and valleys, those are set distances, but if I start moving towards it, I can crowd those peaks and valleys closer together as I walk towards you. Okay? And the people I'm moving away from, the peaks and valleys will get further and further away. Okay? Let me do it a little louder and see if you can hear it. You hear how it goes higher?
Yeah.
Hear it? I feel like I'm in service.
Are you raining handbells? Is that what you're doing?
The holy water.
Oh,
Okay. So, if I was moving, if the source of the sound moves towards you, what happens are the peaks and valleys will be closer together as I go towards you. And so, because the peaks and valleys are closer, the wavelength is shorter, it's actually going to be a higher frequency. So as I move towards you, you're going to hear a higher frequency. People I move away from are going to hear a lower frequency than what it really is. Okay? The cars driving by you, NASCAR, you hear that meow. That is exactly, this is called the Doppler effect. Okay? You would hear the sound of the engine by itself revving. But as that sound comes towards you and going at a much higher speed, the frequency and the pitch of that engine is a lot higher. As soon as it goes past you, now it's moving away from you and the pitch is going to be a lot lower. So that meow is a higher pitch as it comes towards you, and the lower pitch once it goes past you. Okay? So that's the idea with the Doppler effect. Okay?
Hey, what Doppler train lets us light? Like if you're traveling close to the speed of light, trying to do?
Yes, there's something called Doppler Shift as well, when they talk about the speed of light and relativity and all that stuff too. Yes, sir?
You make that car sound again.
You like that? Meow, like that? You can now take that off of YouTube and make it your ringtone. All right.
Oh my God.
Here's another way of thinking of it. Here's a frequency by itself if you just heard the engine. Or if you're in the car, somebody here would hear it as a higher pitch. Somebody here would hear it as a lower pitch. For all the same sound.
It's kind of like when you hear an ambulance coming through.
Yeah, it is. It is. This is also what a radar gun does. When they shoot a radar gun at you, it shoots a frequency at your car, okay, a certain frequency of the radar. When it bounces off, it will be that higher frequency. Whatever your car is going will make that frequency bounce off at a higher frequency. So all they do, a radar gun will shoot out a frequency they know they're shooting out, and when it comes back, they can tell the difference in the frequency and then figure out how fast you're going. Okay? So then they have things called radar jammers, which are completely illegal. But what happens is, somebody notices a radar gun is being shot at you, and they send off all these other radar signals. Of course, they just get arrested for having all these crazy things going on with the radar jammer, and you get arrested.
Yeah, I think you get a ticket.
Yeah.
Yeah, because one of my friends has one, and when you shoot on you, it makes like a loud beeping noise, so you know you're getting targeted.
Oh, really?
Yeah.
Yeah. So, anyway, but that's what radar does too. It's the same idea. It's the Doppler effect. Okay, I am done there, I believe. We'll talk about that next some other class. Yes, Paul.